Okay. Now, kind of reviewing what we've said earlier, but not in as much detail. Critical point of f of xy occurs when? Well, when the x derivative is 0 and the y derivative is 0, because in that case you've got a graph of a function, okay, about like the bottom of a paraboloid, okay? Now, fx, you hold y constant, and your paraboloid is cut in such a way that you have a parabola within that plane, and you cut it in the holding x constant in the y direction, you have another parabola. If it's an elliptical paraboloid, the parabolas will have, one will be narrower than the other. If it's just a straight paraboloid, the parabolas would be similar. And their vertex would be at the same point, and that's the point at which fx is 0 and fy is 0, because of course at the bottom of the paraboloid, at this point at the vertex, you move in the x direction, everything's level. You move in a little bit in the y direction, and everything is level. Your tangent lines are both parallel to the xy plane. Within the plane that you get when you slice the thing, at the vertex of each parabola, your tangent line would be horizontal. So the tangent plane then would be horizontal, and you would have a relative minimum. If the parabola is upside down, it would be a relative maximum. fx is essentially the slope as you move in the x direction. Fy, essentially the slope or the rate of change as you move in the y direction from that point. Okay, well, the only way a relative maximum or relative minimum can occur would be at a critical point. Okay. However, that doesn't ensure that a critical point where fx and fy are both 0 is going to be a relative max or min, because you also know that you can have a saddle point. Okay, the function can be like this if you cut it in the x direction with a y equals constant plane, a plane parallel to the xz plane. Well, in this direction, cutting it parallel to a yz plane with an x equal constant, it could be like this. That'd be like a saddle. Okay? So, critical point can easily be a saddle point. In both cases, here you have a parabola, you got the vertex, and the tangent line is horizontal. And here you've got a parabola, vertex at the same point, tangent line is horizontal. You have fx equals 0 and fy equals 0, but you don't have a relative max or min. You have a saddle point. Okay, well, now, if the critical point is a max or a min, it turns out that fxx and fyy got to have the same sign. Okay? And that's, again, either it's like this and this in the two planes, in which case both second partial derivatives would be positive, or it's like this and like this, negative partials. In both cases, they have the same sign, and if they have opposite signs, well, that's, one's positive and one's negative. There's your saddle point. So if the signs are opposite, you have the saddle point. Now, we make a big jump and make a sort of mathematical statement here. A max or min then requires that fxx, x's and s's are getting here, fxx times fyy, your second partials with respect to x and y, when you multiply them, it's greater than or equal to 0. Now at this stage, I said, well, why is that? And somebody said, well, it's because if they're both negative, you're going to have a positive. If they're both positive, you're going to have a positive. And then this astute individual said, but what about that equals 0 thing there? Well, I was saving that, but since it was asked, I went ahead and explained it. If you have, let's get the right word because I called it a cone instead of a cylinder today. I caught myself, and then I had to search out the word. But let's say you have a parabolic cylinder, okay, a parabola. When you cut it with an x equals constant plane, and the parabola is the same for every plane. So you basically have a long trough, okay? And every parabola that you get when you cut this trough has a vertex, and the vertices just run along a straight line right along the bottom of that trough, don't they? Well, every point there in that trough is a relative minimum. There's no point near any of those points where the and I'm not sure I've been saying maximum and minimum, right? But okay, let's not worry about that. You know how that works. There's no point near any point at the bottom of the trough that's lower, so it's a relative minimum. But the fx in this direction would always be 0, wouldn't it? Now the fy would always be positive, giving you a minimum. And I think I might have said gives you a maximum, but I know better, and so do you, so yeah, kind of ignore that. Whatever I said up here. So that fxx would be 0 in this case, but you'd still have a minimum, okay? Now, it's also possible that one of these is 0, but you don't have a minimum, okay? I don't want to wave my hands over that example, but you can think of an example where that might be. So, anyhow, that kind of shows you that it could be, if this product is 0, that you still have a minimum, okay? But it could be, if this product is 0, that you don't have a minimum or a maximum. Okay. Now, I say then, even if both of these have the same sign, fxy might have a different sign. That means you take a saddle point, okay, where you have this in the x direction and this in the y direction, and you turn that saddle point 45 degrees, and it's very possible that you have this in this direction and this in this direction, or the opposite, this and this. Could be either way, depending on the shape of your saddle. So what you have to do is you have to check not only this direction and this direction, you've got to check directions in between. So what we do is we do fxy, which checks the rate of change in a combination of the x and y directions. Okay? And fxy might have the sign opposite to fxx and fxx and fyy. And if that opposite sign is big enough, that would cause the thing to go into a saddle point. That would be evidence that that would determine that we do have a saddle point. Okay? Now, our ultimate test then, to see if this fxy, when it has a sign opposite to these two, to see whether that causes a saddle point, is simply that, well, okay, if we have this condition where this difference is greater than 0, it means your fxy is not big enough to make this negative. In this case, we'll have a max or a min. Okay? So, you take the product of fxx and fyy, subtract the product of fxy with itself, which you'll probably see written down as fxy squared, but I wanted to write it this way to see that you have a product of 2 second partials here and a product of 2 second partials here. Okay, if I put the square in there, it's less obvious you're doing a product of 2 partials, and it's less obvious that you're doing kind of a fair comparison of these partials with this partial. Okay, anyhow, if the fxy isn't big enough to make this less than 0, then, or less than or equal to 0, then you're going to have a max or a min. If it's big enough to make this difference negative, then you have the saddle point. And if it's equal to 0, you can't tell what you got. You can't tell whether you have a max, a min, a max min, or a saddle point. Okay, you might have either, you might have neither. Okay, so you can't tell anything if it's equal to 0, and if it's equal to 0, you got to do other things to figure out what you have. And usually you can do that, and we'll talk a little bit more about that, but we want to get this general scheme for maxima and minima, and then build around that. Okay, so that's the general test for maxima, minima versus saddle points.